Okay, we've seen that if we look at unit tangent vectors at equal time intervals, we can depict the changes in the unit tangent vector for each time interval, but that doesn't really indicate by itself how curvy the path is between 2 points. Clearly, we would say that this path is curvier here than it is between here and here, but that's not really indicated by the changes in the unit tangent vectors. On the other hand, if we sketch the unit tangent vectors at equal intervals, we do get what's going to turn out to be a pretty good indication of how curvy the path is. So we draw our unit tangent vectors at equal distance intervals. We draw the unit tangent vectors with a common initial point, and we depict them on the arc of a circle where it's understood that we've got our T1 here, our T2 from here to here, T3 from here to here, T4 from here to here. Our change in T between point 1 and point 2, well, right here, here's our delta T 1, 2. So right here, I will depict a vector and try to do this kind of carefully and keep things proportional. Here's our delta T 1, 2 on the scale of the unit tangent vectors as they're depicted here. Our delta T 2, 3 is going to go from point 2 to point 3. It's going to just be a little vector much shorter than our delta T 1, 2. You can't even really see it, it just looks like a red smudge, but when we draw it up here we'll see that we've got a delta T 2, 3 that's much shorter than our delta T 1, 2. And of course, between here and here, this is not a very curvy path. Between here and here, we see that the path is certainly curvier. And then between point 2 and 3, we could have a between point 3 and 4, we would have a delta T 3, 4 that's clearly about the size of our delta T 1, 2, but in the opposite direction. And we could draw our delta T 3, 4 here. Yeah, let's draw it on this side. Now I drew it on this side just to keep it separate from some of the other writing, but I did actually draw it on the side in which the side that you would look at if you were looking toward the inside of the curve. These vectors do in fact indicate average curvatures, and if you think about it, it should make fair sense to you that in some way these are related to the average curvatures, and we would say that the curvature, and I'll go ahead and use a kappa 1, 2 bar for the average curvature between point 1 and point 2 would turn out then to be our delta T 1, 2 divided by how far we move along the curve between point 1 and 2. And our curvature between 2 and 3 would be, our average curvature between 2 and 3 would be this vector divided by how far we move from here to here. And actually it would be the magnitude. Let's be safe here and say the magnitude of our average curvature would be this. So when we define the average curvature, we're going to define it to be the change in the unit tangent vector divided by the distance. And it's not hard to see that in the limit as delta t goes to 0, that's going to be what? The derivative of our unit tangent vector well, I'm going to write it this way then. Derivative of the unit tangent vector times the rate at which our position is changing. Derivative of the unit tangent vector divided by our speed along the curve. Or the derivative of our unit tangent vector with respect to how far we have moved along the curve. And we'll work this out in the next, starting in the next clip. We'll make a formal definition. But here's a plausibility argument and an idea of why we define the curvature the way we do.